Alright, so today we're going to look at natural logarithms, and we're going to be looking mainly at just the derivatives and integrals, and we're going to start, of course, with the definition of a natural log. So natural log is equal to the integral from 1 to x of 1 over t dt. Now, if we look at that, the 1 over t looks like this. And we're going to start at 1 here. Now, as we go to x, remember that's going to be the area under the curve. So x may be off in this direction. So we might be talking about an area over here. So that, of course, would be positive. So anything over 1 is a positive logarithm. We're used to that. If it goes backwards, then we have a negative. If x is over here, we have a negative area because we went backwards from 1 to x. That would give us a negative logarithm. So anything less than 1 would be a negative logarithm. And of course, we can't go to any negative, we can't go to 0 because there's an asymptote here, and we can't go past that because then we have a discontinuity. But once we have this definition, then we can take a derivative relatively easily. So we can take the derivative of natural log of x equals the derivative of the integral of 1 to x, 1 over t dt. Well, that's the derivative of the integral, so if we use the second part of the fundamental theorem of calculus, that's going to equal 1 over x. We could do the chain rule if we needed to, but x is just going to be the chain rule of 1, so we don't need that. So the derivative of the natural log of x is 1 over x. Not bad. If that's a function, so if it's natural log of something, say it's a function of u, then we have the natural derivative of the natural log of some inside function. That's just going to be 1 over whatever's inside times the derivative of the inside. And that is just the chain rule. Okay, so let's practice that with these examples here. So we have the derivative of the natural log of 2x, 2x being the inside function. So it's going to be 1 over whatever's on the inside times the derivative of the inside. The derivative of 2x is 2. Then we simplify. The 2's cancel out, and we're left with 1 over x. Make sure that x stays in the denominator. Don't cancel and then leave me with x. We still have a fraction. Okay. Next one's just as easy, just a little more complicated. Derivative of the natural log of x squared plus 3 be 1 over x squared plus 3 times the derivative of x squared plus 3. That's going to be 2x. Simplify, that's going to be 2x over x squared plus 3. And we're done. Okay, x's don't cancel because there's not a common x in every term. And that's it. The bottom here I provided some properties of logarithms just in case y'all forgot them. If you have a product inside of a logarithm, you can take the log of each factor and add them together. If you have division instead, you can do subtraction. So addition and multiplication go together, division and subtraction go together. Reciprocal rule, again, is very similar to the quotient rule. You can write this as in several different ways, but it is just the negative natural log of x. And then you've got the power rule. And this one is probably the most powerful because the whole idea with logarithms is we need to be able to get that exponent down to the level ground so we can solve with it and mess around with it and do all kinds of things with it. So we need to be able to get it down. So that's one way. And remember, this can also work in the other direction, that we can start with something in front of the natural log and we can bring it up to that. One other note is to remember that this is the whole thing. So it's natural log of the whole thing to that n. So something like natural log of 2x squared doesn't work. Natural log of 2x squared like that does work. There is a difference. Okay? So this does not equal 2 natural log 2x. So moving on, I'm going to come back and do the logarithmic differentiation in another video. That was derivatives. Now we're going to look at integrals real quick. Integrals is pretty much the same thing, just going backwards. So instead of, it's just a new pattern for us to find. So the integral of 1 over x dx, that was our derivative of the natural log. So when we find that, we get the integral of the absolute value of x plus c. It has to be absolute value because we only can take logs of positive numbers. Of course, that's so basic we rarely see that in that form. Usually it will come in the form of a u substitution. So it will usually look like this. But this also might clue you in on why you never saw the integral of x to the negative 1 dx. If we try to use it as the power rule and add 1 to the power, we would add 1 to the power and get 0. Then we'd try and multiply by the reciprocal, and then we would blow up the world and have a bad day. You can't divide by 0. So that was always an issue. But turns out it's because it's not a power anymore. It's not a polynomial. It's actually a logarithm. So that's if you see 1 over u. The integral of the natural log of x dx, we cannot do this yet. It requires a whole nother technique that we're not to yet. We will get to that in Calculus 2. Maybe at the end of Cal 1 I might show you, but we don't have the technique yet. But if you see natural log of x in an integral, you're going to let u equal natural log of x. That might get rid of it so that you can get it down to a pattern that you recognize. Okay? So let's look at this definite integral here. The integral from 0 to 2 of 2x over x squared minus 5. We don't have an inside function per se, but now because of natural logarithms, we can use the denominator as our inside function. So we can say u equals x squared minus 5. Du is 2x dx. We make our substitutions and we get the integral of 2x dx becomes du, so there's our du. X squared minus 5 is u, so there's u. Our 0, when we plug that in here for x, we get 0 squared minus 5, so this is minus 5. Plug in 2, we get 2 squared, which is 4, minus 5 is negative 1. Plug these in, and take the integral. Integral of 1 over u is the natural log of the absolute value of u. We're going to evaluate that from negative 5 to 1. So we get the integral, or we get the natural log of the natural absolute value of 1 minus natural log of absolute value of negative 5, which is the natural log of 1 minus natural log of 5. The only one I really want y'all to make sure y'all have memorized is the natural log of 1 is 0. Because remember the definition, it's the integral from 1 to x. If we go from 1 to 1, that's a 0 area. So that's going to be minus natural log of 5. This is totally acceptable as an answer. You of course might find the decimal approximation. You might also use your properties, and you could do natural log of 5 to the negative 1, which is also equal to the natural log of 1/5. So you might see somebody else might have a different answer, the book might have a different answer, but it all is the same thing, just looks different. Here's an example with trig. Again, we don't have an inside function, it doesn't match any of our patterns, so we have to look around for u substitution. Here, we'll look at our denominator, u equals 3 plus sine x. We like that because the 3 is just going to go away. So du is cosine theta d theta. We do our substitution. We have a 4, so we can pull that 4 out front. Cosine theta d theta is just going to be our du. Our denominator becomes our u. That's what we said right there. And we do our substitutions here. Sine of negative pi over 2 is going to be negative 1. So 3 minus 1 is 2. Pi over 2, sine of pi over 2 is 1. 3 plus 1 is 4. So this becomes 4 times the natural log of the absolute value of u from 2 to 4. Plug that in, we get 4 times the natural log of 4 minus natural log of 2. I didn't put in my absolute values because they were already positive. We can go ahead and combine this. Again, this would be okay most of the time just to show that you finished the problem, but it simplifies quite interestingly. It's 4 times the natural log. This is minus on the outside, so when we combine it into 1, it'd be 4 over 2. Put a little line here. This would be 4 times the natural log of 2. That's not too bad. We could bring it up as an exponent, 2 to the 4th, the same as natural log of 16. That's not too bad. And then, of course, the decimal approximation is 2.73 or 0.773. Now, because of the natural logarithm, we can actually do the integrals of tangent and cotangent now. We haven't been able to do those before. So let's look at tangent. If we consider tangent as a fraction, then we have the integral of sine x over cosine x dx. Well, no, doesn't fit a pattern, doesn't have an inside function, but we can use that denominator. We're going to let u equal cosine x. So du is negative sine x dx. So we'll throw a negative sign in there to balance it out. We need a negative sign in front. So we have a negative integral. Negative sine x dx becomes our du. Cosine x becomes u. We recognize that to be the natural log of the absolute value of u plus c. Substitute u back in, and we get negative natural log of the absolute value of cosine x plus c. So the integral of tangent is this. Guess what? You get to memorize this. If we do the same thing with cosine or cotangent here, it's very, very similar. We get the integral of cosine x over sine x dx. We let u equal sine x. du is cosine x dx. We don't have to worry about negative signs here. So we get the integral of 1 over u du, which is the natural log of absolute value of u plus c, which is the natural log of the absolute value of sine x plus c, and that is the integral of cotangent dx. So again, you need to memorize this as well. Now you have all your basic 6 trig functions, and it just took all year to get there. So the way I memorized these was I remembered which one was on bottom, because I remember that natural log always deals with the thing that's on the bottom, and that's what I stuck into the absolute value. And then I remember that the derivative of the cofunctions always had a negative sign, and so that's where the negative sign went.